Here we have several groups that could be substituents at the aromatic ring. What I'm using here is the abbreviation for the aromatic ring, like the phenyl ring. So strong activators, if you have directly attached to the ring the OH, like in the case of phenol, that's a strong activator. Remember that you always can do resonance. But what I want to point out is, say in all of these, you can do resonance towards the ring, therefore making this a richer in electron density. That's why they are activators. Make the nucleophile stronger. That's why nucleophile, the aromatic ring, by having the more electron density at the ring. So, I want you to analyze the following effect. So when we have, and I go back to the anisole example, when we have anisole, we said that we can do resonance, and here you will put, say, a negative charge here, and you can keep moving that. And you will form resonance structures in which you'll be having more electron density in the ortho and para positions. But that is a resonance effect. So I'm going to name that, since this is richer in electron density at the ortho and para positions here, when you have anisole, let's explain something. We said that this is due to a resonance effect. So we're going to say that this is donating electron density to the ring by resonance, so a plus R effect. However, we know that here between carbon and oxygen, there is a difference in electronegativity, and the dipole would be pointing towards the oxygen. That is to say that the dipole is in this direction. So it is removing electron density by induction, but overall, the predominant effect is resonance. So again, despite that the oxygen is more electronegative than carbon will, I say, withdraw electron density, the resonance effect as donor is predominant in these groups are activators. And then let's see what happens. So in here we have moderate activators, and we see here an ester, amide, and this is an N-substitute amide in an ether. But let's get to the example of the ether ester. So I did with phenol and the phenolate, for example, the same, and with aniline. So you will have atoms more electronegative than carbon. So the dipole makes that all of these will have an effect, say, electron withdrawing by induction, but they will be electron donors by resonance, and that is predominant, this effect, making them activators. But analyzing what we have in the second series, let's draw an ester. So say that I have, this is but the ester of benzoic acid, so this is methyl benzoate. So now, you still have, now, but now, that's a bad example. I drew the ester actually the opposite that I wanted to draw it in that example. But I'm going to go back to that because the effect is different. So I'm going to draw it as is here. So the oxygen here directly attached, and I'm going to have, that's a different ester, that's phenyl acetate, for example. Okay, in that case, we still have the O directly attached to the aromatic ring, but we have this dipole here. That dipole points towards the oxygen. So that is an electron withdrawing effect, so still would be minus I. Now, but I do have resonance effects, so similar to what we explained before, we can still do this in place that negative charge at the positions that are ortho and para, so ortho and para to that substituent. But We can also do resonance structures towards the carbonyl group instead of doing the electron delocalization toward the ring. So we have this possibility. So in other words, having that opportunity, this group is not as as effective donating electron density towards the ring because of that, say, electron attracting or withdrawing effect of the carbonyl nearby. So that makes this group less effective electron donor by resonance toward the ring, because some of that electron density is being delocalized toward the carbonyl. So all of these that have, yet notice an atom that has lone pairs attached directly to the ring, so you can do this, and they are activators, but not as strong because you have the contribution of that other effect. But still, the plus R effect, so donors by resonance, is predominant over the minus I, so electron withdrawing effect. And finally, the alkyl groups, they're now doing resonance when you have, but that effect is by, say, hyperconjugation. That's a metal group. We're now doing resonance here. So that is to explain why when we have an ester like that, or that works also in the case of the amide, for example, here, why that is a weaker electron donor to the ring, so weaker activator. In this case, we're going to classify that as moderate. The weakest are the alkyl groups. Next, we're going to be studying other groups that are actually not activators, but deactivators in another video.